Hello, Assalamu alaikum. My name is Muhammad Abu Saeed. I welcome honorable examiners to my FYP presentation. So, my FYP topic is peer-to-peer solar energy trading for rural communities. So, this is the table of content I will talk about throughout the presentation. First of all, I will give a little bit introduction and background information about the topic, and then I explain about the problem statement and objectives. And then I talk about the methodology and result. Finally, I conclude my presentation. The statistics from renowned website Access to Energy, globally around 13% of the people still have no access to the electricity, which correspond to 22% of the world's rural population, 3% of the world's urban population. This number is much more bigger to the third world developing countries, which leads to the people to use either fossil fuel or renewable energy as their primary source of electricity. So it is clear still a big number of people no access to the utility. Because of the reason I mentioned in the previous slide, the number of small distributed generation like small PV system is significantly increasing. A very small country from Bangladesh already installed 4 million plus solar home system, whereas 2.5 million houses and 45,000 commercial buildings in Malaysia already installed solar PV system. So now the problem is these 4 million solar home system from Bangladesh are losing a very significant amount of energy every day. The number is 60,000 kilowatt hour every day due to the insufficient storage capacity. This number of the energy can be used to power 2.5 million more peoples. So now the concept is very simple. A single solar home system can be connected with neighbor systems so that they can share and sell their excess energy to the neighbors. This is the problem statement. Since in the remote villages they using small system, so in the peak irrigation time, so uh, they losing the surplus generation of the system, and then they don't have any choice to use more loads. So limited demand flexibility is the problem. So self-sufficiency, self-consumption. So these problem statements inspire to the objectives to investigate a grid solar PV system, to formulate an algorithm for energy sharing, to design and DC energy sharing system. These are the objectives covered in this project. In this section, I will discuss about the methodology. The project has divided into two parts. In the first part, an automotive energy sharing system has presented. In the second part, uh, the feasibility of P2P will be discussed. This is the system architecture of individual solar home system, how they interconnect with the network. So to design the effective automotive energy sharing system, the solar home control system architecture has divided into several blocks: solar panel blocks, charge controller blocks, self battery blocks, and self load blocks. In the charge controller blocks, microcontroller use along three DC to DC boost converter to control the power flow from solar panel into the appropriate direction. So in this project, a battery controller model in MATLAB Simulink, and also a automotive energy sharing system designed in the Proteus. Later I will show the design. As I mentioned in the previous slide, microcontroller used to control the power flow from solar panel to appropriate direction. So this is the algorithm to design the microcontroller. Initially, microcontroller will check all the condition. If panel voltage is available, the panel will supply to the load. At the same time, microcontroller will check the battery state. If battery's charge of state is less than 90%, battery will charge from the solar panel. Otherwise, uh, the extra battery panel voltage will go for sharing. On the other hand, the battery condition is checked. If the significant amount of battery voltage is available, battery will supply to the load. Otherwise, the microcontroller will check the grid availability. So this is the basic concept of the algorithm. So this is the model to validate the feasibility of P2P, where I use very renowned PV siting tools, PVSys and Homer to collecting all the necessary data. So now I explain the result, what I achieved in this project. So this is the simulating model of battery controller, what I mentioned in the methodology. So I use DC voltage source as the solar panel. This is the load for all sources. This is the bidirectional DC to DC converter, and this is the battery. Now I explain the simulation result. When source is available, source will supply to the load, as well as source will charging the battery. So battery will be charging mode. When there is no source available, the battery will feed to the load. So obviously the battery will be discharging more. So this is the simulating model in MATLAB. So this is the footage simulation of energy sharing system. So DC source as a solar panel. This is the battery system. This is the DC grid network. These are the four relay switches to control the power flow. So I use a potentiometer to show the all scenarios. This is the energy sharing system simulation result. In this section, I will try to explain the feasibility of P2P. So this is the yearly data of 4 households before they connected to the P2P. So for household 1, they have a total deficit of 9.6% of their total demand. For the household 3, they have 36.4% of their total demand. Household 4, they have 1.1% of total demand. At the same time, household 2, they have 19.6% of their total supply. For the household 4, 42.6% of surplus as their total supply. So this is the 4 household yearly data after they interconnected each other with P2P. So for the household 1, total deficit reduced to 0%. For the household 3, the total deficit will reduce to 7.7% of their total demand. For the at the same time, for the household 2, the total excess is reduced to 6.7% of their total supply. For the household 4, the total excess is reduced to 0% of their total supply. This is the comparative yearly data of solar home system and when they connected to the P2P. So total deficit of 13.53% for the solar home system is reduced to 2.37% when they connected to the P2P. So this reduction increased the self-sufficiency of the community of 11.16%. At the same time, the total excess 22.94% reduced to 9.28%, which is increased the self consumption for the community. In conclusion, it is clearly seen that the community can increase their self sufficiency from 13.53% to 24.69% when they connected to the P2P. In the same time, they can increase their self-consumption from 22.94% to 36.64% when they connected to the P2P. That is the end of my presentation. Thank you for hearing me.